So for the second part of the lab, we're setting up a basic intensity modulator using our liquid crystal cell, which is right here, and it's driven using the function generator, and we're using the oscilloscope to determine that we're running at a safe frequency voltage and with no DC offset. So we have cross polarizers on either side of it, so they are aligned to be exactly shifted so that if this cell was not here, there would be minimal transmission, and that's aligned with respect to the linear polarization coming out of the laser. And then we aligned the liquid crystal cell to be approximately at 45 degrees by maximizing it with no voltage going through it. At that point, we actually went through and measured different amplitudes up to 10 volts to get a transmission curve versus voltage, and then we also placed it at the maximum transmission and rotated through to observe the effect of rotation at max. So previously we used a half-wave liquid crystal cell, but then we also had a little bit of extra time waiting for the other setup, so we did a full-wave liquid crystal cell and we observed a different plot, which you'll see in our results section. In the first part of the lab, we're using the Axometrics polarimeter to measure the characteristics of our liquid crystal cells, and we did this for both a full-wave and a half-wave. And we did the half-wave at two different wavelengths. We did red at 660 nanometers, and we did the green at 532 nanometers. Also, what we first had to do was calibrate the system for each wavelength that we were using. So what we did was we had to adjust the gain in the back of the detector here. We also had to adjust measure the dark current and run the calibration in the software. And so what we did for actual measurements is first we would orient our liquid crystal cell so that the retardance orientation was approximately 0 degrees using the software at 1 volt peak to peak. And we scaled from 1 to 10 volts peak to peak in increments of 0.25 volts. And we measured all of the polarization characteristics using the software for the system, which reads out basically everything, including the Mueller matrix, retardance, dye attenuation, and depolarization.
The Mueller matrix is a compact description of the polarization characteristics of an element. It is multiplied by the input Stokes vector, which is the polarization state of the light, and the output Stokes vector is the resultant polarization of the output light. The Poincare sphere contains all possible polarization states as a point on its surface. There are three parts to a polarimeter: the generation section, the test element, and the measurement analyzing section. The generation section contains a linear polarizer and a wave plate that rotates to create every type of polarization. The analyzing section works exactly the same, but measures the amount of light contained in each individual polarization state. The test element is placed between the two, and the light is passed through it. Liquid crystals are not as organized as solid crystals, but have orientation. The orientation gives them retardance and polarization characteristics. By applying a voltage across a liquid crystal cell, we can twist the crystal structure, changing the retardance and polarization of the cell.
So using the axometric polarimeter, we were able to collect data and plot the retardance orientation as a function of the peak-to-peak voltage that we were driving the liquid crystal cell with. And we did this both with the half-wave LCC and the full-wave LCC at two different wavelengths. Now, you can see that the retardance orientation, when it's unrectified, flips by 90 degrees. And this occurs at the same time that the retardance magnitude wraps, which we'll see in the next slide. Now, you can see in the second plot here on the right side that the retardance orientation flips back and forth rapidly between plus and minus 90 degrees. And this is just a jitter in the system that's effectively the same measurement, so there's no wrapping occurring when those flips occur. So here we can see the unrectified and rectified retardance magnitude as a function of voltage, and you can see how the rectified voltage flips back up. So on the left side here we have the technical specification that came from the Thor Labs website. We're comparing this to our own data. There are a few differences between these two plots. First of all, the wavelength that we measured at was slightly different than the given wavelength from Thor Labs. Second of all, the voltages. On our graph we plotted versus peak-to-peak voltage, but the Thor Labs did not, and so essentially our 10 volts is the same as their 5 volts. Also, the retardance in Thor Labs was measured in waves, whereas we have plotted retardance in degrees. And so below here I have an explanation. The 0.6 waves that Thor Labs measured at 0 volts is equal to 216 degrees, which is pretty close to what we have, so that's good. Now their 0.05 waves that's measured at their 5 volts, which is the same as our 10 volts, measured 21.6 degrees, where we have closer to 47 degrees, so that's a bit off. With the intensity modulator that we built, we were able to plot transmission versus peak-to-peak voltage. And here we did this with both the full wave and the half wave LCC. And you can see that the full wave one has this peak, and that occurs when the LCC is acting as a half wave plate with a retardance of pi. And you also get that similar peak with the half wave LCC. When you get half wave retardance of pi, you get a maximum. Now the half wave one does not drop down to 0, and that's because there's no opportunity for it to act as a full wave plate. And that's when you would have a minimum. You can see with the full wave LCC, when you get a full wave of retardance of 2 pi, then the cross polarizers will result in no light getting through, and that you can see occurs at this dip in that plot. Now below we have a plot of the orientation of the LCC versus power, and that was, both of these plots were taken at maximum transmission for the respective LCCs. And you can see that even though the LCCs are different, they still have the same characteristics of orientation versus power.